Thank you everyone for coming. My name is Sunjay. I'm here to talk about constant time programming in FaCT. This is work that I've been working on with a whole host of fellow collaborators. So before I get into what constant time programming is or what FaCT is, I want to talk a little bit about timing side channels. So say you have a cryptographic routine, and it takes an encryption key, it takes some unencrypted plaintext message, and you want it to produce your encrypted ciphertext. And what you don't want this cryptographic routine to do is leak your secret data. So you don't want it to leak your encryption key or your plaintext message. The issue is that if it's not implemented carefully enough, the crypto routine could have minute timing differences based on the secret data. And an attacker that is clever enough can measure these timing differences, and from those timing differences, extrapolate the secret data. And so one of the ways of combating these timing side channel attacks is through constant time programming. Just a quick note, when I say constant time, I don't mean that the program takes the exact same amount of time to run every single time. It's a little bit of an unfortunate misnomer. What constant time means is that the time that it takes for such a program to run is independent of the values of any secret data. So I'll walk you through an example of what constant time programming looks like. So a little bit of background first on cryptographic padding. Most encryption algorithms deal with messages in chunks called block sizes. So if you have some message and it doesn't fill out a full block size, when you encrypt it, the encryption algorithm is going to pad it out so that it fills a full block size first. And so when you decrypt it, you have that message, plus you have a bit of extra padding that was there just to pad it out to the block size. So what we're going to do is we're going to write a function that removes this padding after decryption. So we're going to write this function. It's going to check for valid, in this case, PKCS7 style padding. In this style of padding, each byte of padding holds the padding size. So in this example, there's 5 bytes of padding. So each byte holds the value 5. And we're going to have this function replace each byte with null and return the total padding length. Or if there was invalid padding, it'll return an error. And the key here is that the buffer contents, since they came from the decryption routine, the buffer contents should be considered secret. And that includes the padding values. So here's a naive first implementation in C. I'll walk you guys through this. We look at the final byte of padding to determine the overall padding length. And for each of those bytes, we're going to check whether it's the proper value, and we're going to zero it out. And provided nothing went wrong, we'll return the padding value at the end. So let's say each iteration through the loop takes 10 microseconds. So all in all, this function takes about 50 microseconds to run. But what happens if we have an invalid byte of padding in the middle of this? Then we're not going to take the full 50 microseconds to run. We're going to end up returning early. And this, an attacker can look at this timing difference and figure out whether or not the padding was valid, because if we return early, then there was invalid padding. This is known as a padding oracle and can lead to padding oracle attacks, which can leak your secret key. So this is really bad. And the problem, like I said, is that we're returning early in the middle of this function based on secret data. So what we're going to do is we're going to rewrite this function. There's a host of essentially recipes that one can use to rewrite a program to remove these sorts of problems. So the recipe we're going to use in this case is we're going to create a new local variable. And that local variable is essentially a flag. Instead of returning on an error, we'll simply set the flag to 0. And at the end of the function, we'll check that flag to figure out whether we should return the padding length or if we should return an error code. And so now, even though there's invalid padding, we'll still go through all 5 iterations. So there's no longer this timing difference based on whether the padding was valid or invalid. So that's good. But what if instead of, say, 5 bytes of padding, we only had 3 bytes of padding? Then we're only going to iterate over the last 3 bytes. And now we're only taking 30 microseconds instead of 50. And so now there's, again, this timing difference based on the amount of padding, and thus we're leaking the size of the message, which is more secret data. And the problem this time is that our loop is based directly on this secret padding length. So we're going to use another recipe to fix this. And we know in this specific padding style that the padding length has to fit inside a single byte. And so that means the padding length can be at most 255 bytes. So what we're going to do is we're always going to loop over the final 255 bytes of this buffer. And we're going to check whether or not we're in the true padding zone or not in the true padding zone. And so that way, whether we have 3 bytes, 5 bytes, or however many bytes of padding, we're always going to iterate the same number of times through the loop. And so we no longer have this timing difference based on the amount of padding. Or so we think. So if we dig into this a little bit more, in the true padding zone, we're executing the entire contents of this for loop. But when we're not in the true padding zone, we're falling out of this conditional block, and we're only executing this much code. And so it's not really 10 microseconds. It's maybe something more like 9. And so again, we have a smaller, but still a measurable timing difference based on the message size, and thus based on the padding length. And the problem this time is that we have conditional code based on secret data. So whether or not we're executing code is based on some secret conditions. And this is where things start getting a little bit ugly. So to remove conditionals, you start having to use these kinds of crazy bit hack code. So don't bother trying to parse this. It's not worth it. But the end result of all of these bit hacks is we get the semantic equivalent of the code on the left, but without any of the actual conditional statements, and thus no timing differences. And so now, every iteration through the loop does in fact take about the same amount of time, and we no longer have any timing differences. So this is a final constant time version of this code. And you can kind of see the process it took to get here, so it might make sense now, but if you come back to this in, say, a year, or if somebody else has to maintain this code and figure out what it's trying to do, they're going to look at this and they're going to be like, what is this doing? It's crazy, it's hard to parse, we don't know what's happening. And this is the failure of constant time programming as it stands right now. You may be thinking to yourself at this point, well, why can't we do something simpler? Is it really necessary to do all of this? Why can't we just use the original naive version and, say, implement a random sleep? And so for each individual iteration of this function, an attacker wouldn't be able to determine anything from the amount of time it takes to run. But if an attacker can execute this function multiple times, they can just average out the randomness, and you're right back where you started. So random sleep doesn't work. You could also imagine, well, what if we did something where we execute for 5 bytes of padding, and then we sleep for whatever the equivalent of the other 250 iterations would be. So we have straightforward code, and then we just sleep to whatever maximum value. The problem there is that it's very difficult to determine what the actual max value should be, especially with all of this underlying hardware architecture, branch prediction things going on. And so if there's even a small timing difference, then an attacker can capitalize on that. So sleeping until some max value doesn't tend to work out either. And so you do actually have to do this kind of crazy bit manipulation as it stands right now. And so this is where we currently stand with constant time programming. You have to manually keep track of what is secret, what is public. You can't use conditional statements. You have to be careful with your looping constructs, and there's no real simple solution. And as a consequence, as you can see, it took us multiple iterations to get to this point. It's difficult to write this code, and it's even worse for somebody that has to come back to it at a later point and try to maintain this. And this is actually something that happens in practice. So about a decade ago, there was a timing-based padding oracle attack found against OpenSSL. And this is a screenshot of the patch that was there to fix it. The code after that patch, the fixed version of the code, still had another timing-based vulnerability. So if you've heard of the Lucky 13 attack, this was an attack against, it was a timing difference found in the code that was supposed to have fixed the original timing difference. And even after this patch, there were still more timing differences. And so it took many years for them to finally fix all of the different timing variations until the code was no longer at the point where there was no longer any more timing variation based on secret data. But even then, there was still a bug in the code. It was a padding oracle. It was not a timing-based padding oracle because there was no more timing differences, but it was a database padding oracle. And the fix is literally just this single line. And all this line is doing is checking that the stated padding value does not exceed the maximum possible padding value. And it seems really simple in hindsight. but it was buried among all of this other crazy bit hack code that they were using to remove these timing differences. And so it went uncaught for 3 years, and it took somebody with a fuzzing tool to catch that this was something going wrong. So in practice, constant time code is actually very hard to maintain. And this is exactly where a domain-specific language can help step in. So with the domain-specific language, you can explicitly distinguish what is secret and what is public, have that incorporated into a type system that prevents you from writing leaking code, and we can even have the compiler help you write constant time code, allow you to write something that's clear and concise, and have it transform it into something that's safe. And so this is what FaCT is. We don't imagine FaCT as a general-purpose programming language. It's meant to be a language where you just write the functions you need to be timing secure. So if you have a pre-existing code base, you can write your timing secure functions in FaCT. The compiler will produce a header file, and it will produce an object file, and you can toss those right into the rest of your tool chain, and it just fits easily right in. So what does FaCT code look like? So here's an implementation of that same padding removal function that we were going through at the beginning. Right off the bat, you might notice we have explicit labels. So the contents of the buffer are secret. The return value of this function is secret. And the temporary variable we're using to store the padding length is also secret. So the compiler will check that we're not leaking any of these values. We have some basic memory safety. So we're marking this buffer as mutable, since we're zeroing out part of its contents. And we have a precondition that the buffer is at least 255 bytes long, since we're going to be iterating over those final 255 bytes. And most notably here, we're using conditional statements, and we're using a return statement smack in the middle of this function. And it's totally fine, because the compiler will realize that this is something that needs to be taken care of, and will transform this into constant time code. And this is much nicer to work with than that crazy C crap that we were doing before. And it's totally constant time. And again, this is because we have the compiler using labels and doing automatic transformations. So I'll go over those in more detail. The labels are there to ensure that there is no leakage. There's no assignment from any secret data to public variables. There's no indirect leakage of secret data based on control flow or any other routes. And we can use these labels to prevent secret expressions that may leak in an indirect manner. So like I talked about bounding your loops with secret data. This would be disallowed by the FaCT compiler, because you're bounding your loop with a secret value. But if you're bounding it with a public value, that's totally fine. And inside of that loop, you can have some secret conditions so that you're only doing things when you need to. If you index memory based on a secret index, that can lead to cache timing attacks, which can then reveal that secret data. So indexing memory based on secrets is also disallowed by the FaCT compiler, but indexing based on a public value, again, totally fine. So you could do something where you loop through some public indices and then, again, use a conditional statement to select the values that you want. It's also the case that there are instructions in the architecture that have variable timing based on the operands. So for example, on x86-64 platforms, integer division takes different amounts of time based on the operands. So in fact, we disallow division based on secret values. But dividing with public values, totally fine. Or if you have a constant time division algorithm, you can use that as well. There's also the issue of recursion. So recursion can leak data just like a loop bounded by secret values. The amount of times you recurse may be based on some secret value. In the FaCT language, we just disallow recursion entirely. We haven't found that it's useful in cryptographic implementations we've looked at, and so it's easier just to have no recursion at all. FaCT is, after all, a domain-specific language, not a general-purpose language, so we don't need recursion. So the other part of FaCT is that we can automatically transform this code to be constant time. So all of those recipes that I was showing you where we rewrote our code manually, FaCT can apply these automatically. So for example, if we have conditional statements, if we have some assignments based on some secret conditions, we can transform those into straight-line branch-free code. So in this case, we'll set up these, so the code on the left is FaCT, the code on the right is pseudocode. This would be kind of internal to the compiler. So it would select between different values based on these conditions. We're folding the control flow into data. So if S and S2 are both true, then we will assign 42 into x. Otherwise, we will assign its previous value back into itself. Similarly, if s is true but s2 is false, then we'll assign 17 into x. And if s is true, then whatever value x ends up as, we'll add 2 and assign that to y. And so this CT-select kind of pseudo function can be implemented in an efficient manner. So on platforms that support it, like x86 platforms, there's a conditional move instruction that's known to be constant time. So we can implement this selection operator using a cmove instruction. On other platforms that may not support this, we can use those same bit hacks that we saw in the C code. And so we have this primitive that we can then use to conditionally select values and keep things constant time. So this is one type of transformation we do. Another type of transformation deals with those early return values. So if we have a return predicated on some secret condition, we can transform that such that we have a new local variable that tracks the current return value, and we have a flag that determines whether or not this function would have returned. And we conditionally update those values based on what the current control flow should be. So if s is true and we haven't already returned, then we update our return value with 42, and we set the return flag correspondingly. Then later down the line, if we haven't returned at that point, then we update the return value with 17, and we update our flag appropriately. And at the end of the function, we return our return value. We can also have transformations across functions. So if we have some function that could mutate its arguments, so in this case, we have the function foo that can update the value of x, and it's called inside a secret condition. What we can do is we can transform the function call to take this caller context. So we pass the caller context into the function, and then we update the function itself to use this caller context whenever we need to update one of these externally visible variables. So we get cross-function transformation as well. So this may seem fairly straightforward on the face of it, but transformations can be a little bit subtle. So in this example, we have the condition if I is less than some secret index, then zero out the corresponding index in the buffer. But if I is, for example, out of bounds for buff, conventionally, because this is a conditional statement, we would guard this execution, and we wouldn't touch memory based on I if it's out of bounds for buffer, because it would be greater than whatever secret index. But after transformations, we're always going to be accessing this index I, whether or not I is out of bounds. And this could lead to memory errors, such as a segmentation fault. And that's bad. And the issue is that conditional statements after transformation no longer guard execution. And this is something we have to be careful of. So the FaCT compiler will disallow these kinds of programs by setting up constraints and checking whether, after transformations, we still have these kinds of errors. So we can use an SMT solver, such as Z3, to generate constraints on our program as we're checking them, and check that post-transformation, make sure that we don't have any memory errors or any undefined behaviors. So division by 0 or shifting beyond the width of an integer, we can check for that, and we can check for that knowing the semantics of secret if statements and making sure that this is still the case even after transformation. So we have a safe language. We can also guarantee that post-transformation, the code is constant time. The way we currently do this is we rely on an external verification tool, in this case, ctverif. So after transformations, we take the resulting code, we give it to this tool, and it comes back saying, yes, you are in fact constant time. And so with this guarantees of safety and constant time, you can drop this right into the rest of your code base. And we have features in the language that allow you to do this very easily. So the FaCT compiler can generate header files with function prototypes so that your C code or any other code with a foreign function interface knows how to call the exported FaCT functions. You can call external functions from FaCT as well, provided you give the FaCT compiler an appropriate extern declaration for the function. You can even pass complex data structures as long as FaCT knows the proper memory layout for the data structure. So you can pass structs back and forth between different functions. And the coolest part is that we have libraries for embedding FaCT directly into other languages. So we have currently embeddings for Python and Haskell. So here's a snippet of Haskell code with an inline FaCT function declaration. And this would generate a function choose in Haskell that you could then use as a Haskell function for a constant time selection routine, for example. So I've been telling you all about how FaCT is super great in theory, but how is it actually in the real world? So it must be efficient, especially since we're talking about cryptographic code, and it has to be actually usable, since I've been harping about how conventional constant time programming is not very usable. So we've ported code from several major cryptographic libraries, and we've also conducted a user study. So I'll share some of the results here. This is the performance numbers from one of the OpenSSL decryption code paths. This is the same code path that had all of those problems that I showed you earlier with all of the different timing attacks. So that decryption path is what we measured. So this is measuring throughput, so higher is better. At the very top, you have the conventional C implementation. And just barely below that is our FaCT port of it, where we took the C code, ported it to FaCT, turned all of the bit-hat code into conditional statements to make it a lot nicer to work with. And we're only doing a little bit less than C. We also did a complete port from scratch, where we re-implemented the whole code path in a nicer, more modular way. So on smaller chunks, we're about a little bit better than half as fast, but we quickly catch up to the C code with larger chunk sizes. So it's very promising. We also have the performance numbers for libsodium secret box, and we actually do better than the C implementation in both encryption and decryption in this case. And the reason for that is the C implementation in secret box uses hand-coded assembly for implementing one of the underlying routines, the salsa 20, for accessing vector operations. And so they're using hand-coded assembly, whereas in fact, we expose vector types and vector operations directly as part of the language. And so the vector operations, in fact, will go through the compiler, go through the optimizer, and we generate more efficient vectorized code than the handwritten assembly. So it's a win for us here. So I mentioned we had a user study. We conducted this on an undergraduate programming language class. We had 2 sets of problems for them to do. We gave them code written both in C and written in FaCT, and we had them write short answer responses telling us what the code is supposed to do. And we also had them write constant time code themselves, both in C and in FaCT, based on some specification that we gave them. And the results we found were really good. So students were better able to understand FaCT code than C code. So when looking at FaCT code, they were more likely to be able to correctly tell us what the code was supposed to be doing, as opposed to the corresponding C implementation. When they were writing code, more students were successfully able to write a FaCT implementation than the corresponding C implementation in constant time. We allowed students to submit programming, for writing code, we allowed them to submit multiple times, and we logged what kinds of errors that they had. So if they had syntax errors, or type errors, or security errors. So security error would be they're leaking secret data. And students were less likely to get security errors when writing FaCT code. We did also find that students were more likely to get syntax errors, though, when writing FaCT code. And we chalked this up to FaCT being a new language. It's a little bit different from C, so they had to adapt to that. And we actually improved some of the FaCT syntax based on the results of this user study. So this was actually really useful to us. So FaCT is actually a language in current development. So we have ideas that we're still looking to implement. So I mentioned that we have vector operations as a feature in the language. We would like to look at other cryptographic routines, see what additional features might be useful to have in the language, maybe some add with carry primitives or big num operations or things of that sort. Currently, we're only focusing on the x86-64 architecture, so targeting other backends would be really great. ARM just came out with a new architecture set that has constant time instructions as part of the architecture, so that would be a great thing to target. There's also the constant time WebAssembly specification, which I am also involved in, which is an addition to the WebAssembly spec for constant time programming, so you can have crypto safely in your web browser. And we'd also like to verify the FaCT compiler itself. So prove that the transformations preserve semantics and that they result in constant time code without having to rely on an external verification tool. So that was FaCT. It's a domain-specific language for constant time crypto code. It transforms your code to be constant time, so you can write it in a clear, concise manner, and it fits directly in your tool chain, and it's fast, and it's usable. You can find the source code for our compiler online on GitHub, plsyssec/fact, and it'll also link you to the other repos that we have, so the libraries for embedding into Python and Haskell, and the ported code that we have. So, thank you. So I have one question here. So the question is, can you describe the methods used in your user study a little more? Did you do anything to control for students' programming skill? So the user study, the way we had it set up is we randomly divided students into 2 groups. So all students saw both versions of a given problem. So both for reading and for writing code, they saw both the C version and the FaCT version, but we had them randomly split up between seeing the C version first and then the FaCT version, or seeing the FaCT version first and then the C version. So that should have controlled for any variation in programming skill between any of the groups. I'm not seeing any other questions on Slido, but if any, yes.
You said no recursion, but would there be looping?
Yes, so we have for loops. Right now, we only have for loops, and we have for loops with only monotonically increasing bounds. So that's to help the analysis, so we can check what range the loop variable is in. Yeah.
Have you seen any effects from compiler optimization that work against the constant time?
Yes, so this comes up a lot in C programming especially, which is one of the reasons why we wanted FaCT separate from the C language. So the FaCT compiler produces LLVM code, and we produce LLVM code that, to our knowledge, the compiler does not optimize back into branching code. So we're careful in what LLVM instructions we're emitting. So for example, there is an LLVM select instruction that for 32 and 64-bit values will produce the cmove operation. But if you try to use select for 8-bit values, it'll produce a branch. And so we have to actually use inline assembly for selecting 8-bit values so that we don't run into that. Yeah. Yes?
Are there any efforts then to work with LLVM and potentially other compiler backends to make sure they provide like constant time primitives in their intermediate representations?
Yes, that would be swell. So at another conference that I was at, I actually met with somebody that knows some of the LLVM devs, and he passed along some information. It's something we want to look into, but we haven't been able to reach out to them as of yet. Yes, in the back.
There are some Rust types and code to use also constant time transformations. How would you compare that to FaCT?
I am not aware of the Rust constant time stuff, but we should,
So do you
yeah.
think the type system can be used for the same tasks like you said?
Not entirely sure what you mean. Okay. We should talk afterwards, but yeah. Yes?
To allow external functions, are you strictly relying on the external verifier to make sure that it's still constant time?
Yeah, so right now, the current version of the language, we only allow, so we're a little bit choosy in how we allow external function calls. So you're not allowed to make external function calls within a secret context at all. And even with that, it is possible that even outside a secret context, you pass it some secret value, and then it goes and does its own thing that leaks that value. We currently don't have a way of checking that external code plays nicely and is constant time. We're relying on the developer to know that essentially. So it's a kind of like an escape hatch for like, if you have some really low-level assembly implementation that you don't want to rewrite in FaCT, then you can call out to that. That's essentially what it's meant for. I don't know if there are any other questions, but if not, oh, yes.
Are you also safe from, does FaCT only ensure constant time? Is it safe from other things like, I don't know, copy or something, or does it just?
What do you mean by?
I just like, is it just focused on the constant time issues and maybe?
Yes, well, so yeah, so it prevents timing-based leakages. It's memory safe. I'm not sure what you mean by if it prevents mem copy errors, but.
Just like unbounded, like, does it catch those issues too, or is it?
Yes, so that's going into the memory safety issue.
Okay.
So if the compiler can't prove that your code is memory safe, then it'll fail to compile. I guess along those lines, I should note that FaCT code would not prevent you from Spectre-like attacks. We started this before Spectre blew up. So it is possible to have code that is constant time that is still susceptible to Spectre attacks. So that is outside of our scope. Yes?
For other languages, if you want to bring this idea to other languages, you need some kind of constant time primitives at the bottom to get it done. Is that correct?
Yes. Yeah. So like in fact, our bottommost primitive is that CT select, essentially. So however that is implemented, that being able to choose in constant time between two values kind of builds up the rest of the transformations. So you would need something like that in whatever else you were implementing this in. So I guess that's that. Thank you all for coming. Thank you for the questions.